Right, so we're going to talk about scatter diagrams. There's quite a lot of info today, so and there will be some practice. I'm not going to entitle this scatter diagrams. I'm going to entitle this bivariate data. Bivariate data. I do. Yeah.
Okay.
So where have I put my glasses? Oh, this is going to be fun. Oh well. No, we're not okay. We'll struggle on with that one. We'll find out. It'll be entertaining. Okay. So bivariate data is just data where you've got two variables. All right, that's it. Bivariate data, data where you've got two variables. And so it's the sort of data that we plot on a scatter diagram. And I just want to quickly whiz through some of the basics, but particularly how scatter diagrams at A-level vary from scatter diagrams at GCSE. We've already discussed, haven't we, how how histograms, at GCSE are different to histograms at A-level. Well, scatter diagrams just the same. So firstly, when we plot a scatter diagram, we need to be a little bit more rigorous about what we are plotting on our two axes. And for those of you doing science, well, you all did science last year, you're at a bit of an advantage here, because generally when you've got a relationship between two variables, one of them is in control. And we call that the independent variable. So really, when we do a scatter diagram at A-level, the independent variable is the thing that should go on our x-axis. And then the dependent variable goes on the y-axis. That's the thing which is being affected. Now, I'm not sure with this, I'm not sure whether I completely agree with this as an example, but I suppose yes. If you start breathing heavily, then your pulse will raise. So I guess it's the breaths which is affecting the pulse. Your pulse isn't in control. The pulse reacts to changes, doesn't it? And another phrase that's often used then is the explanatory variable. Is that something used in science? Explanatory variable? Yeah, I've seen that in a question actually. So that's another word for the independent variable. And then the dependent variable is sometimes referred to as the response. The response variable. So you've got dependent and response. So that's the first thing. Second thing then is there's a difference between being asked what's the correlation and what's the relationship. Now this actually existed at GCSE as well. If a question says what's the correlation, then your answer is going to be positive, negative, whatever, and we're used at GCSE to seeing the different options that we've got there, so I suspect you probably don't need to make notes on that. If a question asks about the relationship, then they're expecting more than just saying positive correlation, negative correlation. They're expecting you to put it into context. So in my example here, if it says, what's the relationship, I'd say positive correlation, which means that, and then I'd go on and state the obvious. More breaths per minute mean a higher pulse. Okay, so you've got to mention the context of the problem. So If it asks for correlation, you're just going to say, right, it's a whatever, positive, negative correlation. If it asks for the relationship, then we need a little bit more. We need a little bit more. And then the third thing, which again probably we did talk about at GCSE, is the difference between correlation and causation. I mean, we clearly, with this set of data, we have a clear positive correlation. As the number of breaths per minute increases, pulse is increasing. But is that a causal relationship? Are the number of breaths per minute causing the pulse to increase, or is there something else at play? Now that's perhaps a little bit, I'm not super happy with that as an example, so let me give you a better example, okay? The better example unfortunately doesn't have a graph with it, but hopefully we can see from the data here that when this chap did a little investigation about the speed of his internet, and he did that by measuring the time it took to download a large file, although a 100 megabyte file is not very long these days, you can tell how old this question is. Well, sorry, he didn't do it lots of times. He got lots of different houses to do it, and it compared that with the value of the houses. And you've got a fairly clear negative correlation here. Okay, I mean, we're not going to draw a scatter diagram. We're not going to draw any scatter diagram, so it's a waste of time. But you know, as the time taken to download this thing increases, the house price is decreasing. So you know, in this set of data, we've got you know, time here, house price here. We've got a fairly clear negative correlation. But does that mean that it is the internet speed which is affecting the price of the house? And it can't be, can it? There's got to be something else at play. So, you know, maybe it's a big house with thick walls and they're falling down and that's affecting the house. So, you know, there's all manner of things which might be at play. So don't assume that correlation means causation. And the classic example I always use is if you go to Woolacombe and you look at drinks sold on the beach and sun cream sales in the shops on every day in the summer holidays, you will get a fairly clear positive correlation. If there are more drinks sold, there's more sun cream being sold. Does that mean applying sun cream makes you thirsty? No, there's something else in play. The other thing is going to be the temperature. The temperature is causing both people to go and buy sun cream and buy a drink. So there's something else at play. It's not sun cream, suntan lotion making you feel thirsty. Okay? So correlation doesn't necessarily mean causation, and we just need to look out for that. Finally, and this is where we're going to sort of settle with this, line of best fit. This is the biggest difference between GCSE and A-level. At GCSE, once you had a set of data and you were asked to make predictions for that set of data, you would have drawn a line of best fit by eye. So you would have put your ruler on the page and you would have sort of gone like that and tried to make it go through as many of the points as possible. Or I always say, try and make as many of the points above the line as below the line. We don't do that. Rather than by eye, at A-level, it is calculated rather than drawn by eye. But the good news is, we used to need to calculate it. It was part of the syllabus. It is no longer part of the syllabus. It's dropped off the syllabus. Don't ask me why. It's a great shame because it was a great calculation. But let me show you how it works. But the good news is you don't need to actually do this. So here we go. Let's take a pretend set of data that has a positive correlation. So here we go. I'm plotting some completely made up points that have a positive correlation. So I might put a few. Here we go. So if I'd given you a printout of this and said, right, draw a line of best fit, you would have had a good go, I'm sure. So we've got I don't know, something like that maybe. Maybe I've changed the steepness a little bit, bring it up a bit. It's not bad. What happens at A level, and we don't need to do this calculation, but when you are given the equation of a line of best fit, what they've done is this. They've looked at how far away from each point the line of best fit is in the y direction. Okay? In the y direction. And we have had this problem before with standard deviation, where that means you've got some positive differences and some negative differences. So what they then do is they square each of those differences, which we're representing here by a square. And then what happens is you do a calculation which tries to minimise the sum of all of these squares. So this little applet is showing me what those squares, their area, all adds up to. So I can sort of fiddle about to try and get, if I wasn't far off, was I? I was pretty much there already. But as your line of best fit gets better and worse, you can see that. So what we're doing is we're trying to minimise the errors in the y direction. We're trying to minimise the errors in the y direction. And this method is referred to as the least squares regression line. The least squares regression line. I'm going to write that and then I'll explain, well, hopefully the least squares bit is obvious. So we're still under the subheading of line of best fit, but we don't use the phrase line of best fit. We tend to refer to it as the regression line, but the method we use is this least squares method, where we're trying to minimise the area of the squares. So the least squares regression line. So least squares because of that. The word regression is this idea that in a large set of data, you're always going to get some that's bigger and some that's smaller, but in general, it's all going to average out to a particular value. All right. So if a mother has 5 children, some of them will be a bit taller and some of them will be a bit shorter, but they'll average out. And that's called regression to the mean. And what this line is saying is that, with this set of data, whatever it was, some things were bigger, some things were smaller, but it's all going to average out. And that line reflects that sort of average. So the least squares regression line, we describe it not by drawing it on a curve, on the graph, but with an equation. And it would be really sensible, wouldn't it, to use y equals mx plus c, because that's the way we are used to straight lines being drawn. Sadly, we don't do that. Don't ask me why. When we are describing least squares regression, they use A and B, and it's the other way around. I have no idea why this is. It's one of these historical things. The key thing is that A is the y-intercept. It is the same as C is. So this is still the y-intercept. And more importantly, you need to understand, so that's what y is when x is nothing. That's what y is when x is nothing. And B is still the gradient. It's the number of x's, it's still the gradient. And in this case, that means how much y increases by for every increase of 1 in the x direction. So this is the value of y when x is 0, and this is the increase in y for an increase of 1 in x. So A and B are the equivalents to C and M. I have no idea why. All of this is very much to do with y. All of the errors were measured in the y direction. And that means this line is only used to make predictions for the y value. Because it's minimised the errors in the y direction, it's only used to make y predictions. So do you remember at GCSE where they'd say, yeah, predict the value of this when x is 7? We can do that. We can make a prediction for a y value, but it's not appropriate to do the reverse because this line of best fit has been designed to minimise the y errors. So it's only used to make y predictions. And the other thing is, and this did exist at GCSE, it's only used to make predictions within the range of values that we've got. So do you remember the word that we use to make, which is about predictions outside the range of values we've got? Extrapolate. So we don't use it to extrapolate. We can't make predictions outside the range of values that we have already, okay? So it's only used to make y predictions and only within the range of values plotted. So we are using it to interpolate, make predictions within the range of values we've got, that word we've used already in statistics, not extrapolate, not extrapolate. Right, a lot of talking, for which I apologise. Let's have a look at a question. The questions are really easy. Not that one, sorry, what am I doing? On the wrong page. Okay. So here is an example of a typical question that uses what we've talked about. So we've got a set of data, the scatter diagram has been plotted, we've got a pretty clear positive correlation. Sorry, I need to add another thing here. This is only valid if we've got correlation. So there's no point making predictions. You can't draw a line of best fit if you haven't got correlation. So sorry. So only used when we have correlation. So gestation period, that's how long the baby was in the womb, and its head circumference. We've got a fairly clear positive correlation and a fairly clear independent dependent variable. All right. Size of head is not affecting how long you spend in the womb. It is how long you spend in the womb that is affecting size of head. So independent, dependent. So they plotted it correctly. And we are given the equation of the line of best fit. Okay? So can I ask you to write for me, with this example, what 8.91 tells us and what 0.624 tells us? And one of those makes sense, one of those is nonsense. But can you include units in there? Okay? So what does the 8.91 tell us? And what does the 0.624 tell us? And include units. Include units. One of those two numbers is sort of nonsensical, but still valid, and one of them is useful. I'm taking the register without glasses, so I apologise if I get it wrong. That's the wrong class. So go for it, Harrison. 8.91.
8.91 is just the y mistake.
Say again, sorry?
8.91 is just the y mistake.
So in this context, what would that actually mean?
Oh, when the baby is 0 weeks old, it's got a head diameter of 8.91.
Yeah. Well, not 0 weeks old, but when it's been in the womb for 0 weeks. That's right, yes. So a baby that's been in the womb for 0 weeks, according to this line of best fit, would have a head circumference of 8.91 centimetres. Now, clearly, that's wild extrapolation, isn't it? So that's definitely not valid, but it's an important value, because if you continue this down all the way to 0 weeks, then that would be the y-intercept. So, Laura, what's the 0.624?
How much the head size increases, like, I don't know how much a square would be.
Well, it's not a square, it's 1 unit. So the units on the bottom axis are?
2 weeks.
Well, it's per week. So however they've chosen to label the axes, the gradient is how much per week. So for each week, the head grows 0.624 centimetres. And you know, I can perhaps appreciate that value having a little bit more relevance. Okay, so it is perfectly okay to make a prediction for a baby born at 39 weeks. Let's just check the 3 checks. Do we have correlation? Yes. Are we making a prediction for Y? Yes. Is it within the range of values? Yes. 39 weeks within the range of values. Ben, why is it not appropriate to make a prediction for 30 weeks?
Is that extrapolation?
It's outside the range of values, so it's extrapolation, that's right, yeah. So 39 weeks, good prediction. 30 weeks, bad prediction. Callum, what about using this graph and this line of best fit to make a prediction for a baby born with a head circumference of 31.6?
That'll be for the X.
So we are not using it for Y predictions. Now, okay, it would still give you a rough idea, but that calculation that we just did here, there is an equivalent calculation you can do for the X errors. There's 2 regression lines. On our syllabus, we only have to worry about the Y regression line, but it is possible to calculate a different regression line, which will give you a better estimate. Okay. So there we go. So that's basically all that you're asked to do. You're asked to interpret the meaning of these numbers in context. You're asked to comment on the reliability of predictions, and you're asked to explain why in some cases predictions aren't appropriate. And so what we're going to do, for those of you that aren't here, we're going to make our way through page 65, exercise 4b, but we are not going to draw any scatter diagrams. If you at home want to draw scatter diagrams, that's fine, but we're not going to draw any scatter diagrams. We're going to skip that bit. Okay? Pause. I mean, they're pretty formulaic, aren't they? They're pretty formulaic. So by that I mean they're pretty similar each time. So Helen's wrong, isn't she? She's just done 1.45 times the number of years. She hasn't taken into account this. So actually, with 10 layers of paint it's going to be 14.5, because that's 1.45 times 10, plus 2.93. So she didn't add on the 2.93. Here, so what's wrong? What do you reckon is wrong, Amy, with a gradient of 0.063 from that data?
I was going to say that there's no correlation.
Well, there's definitely not a positive correlation.
So it's negative.
So it's a negative correlation. So remember, this is the gradient. So with a negative correlation, the gradient would be negative. So we expect that to be negative because, and I know we didn't draw the scatter diagram, but you can imagine that this is clearly getting bigger and that's getting smaller. Negative correlation, this will be negative. So Harry, why is it unreasonable to say that because 190,000 is the value of y when x is 0, why is it unreasonable to say what she says there? A house with no bedrooms would be worth 190,000.
No, because that's predicting the value of x.
It is no. We're the number of bedrooms we're using is 0. How many houses with 0 bedrooms have you visited?
Oh, no.
Yeah, so you can be pretty sure that whatever data she used, there were no houses with 0 bedrooms in. I guess you can have an apartment where you put a bed up every night. But yeah, that's extrapolation, isn't it? It's like the baby's head example. Whatever it was with the baby's head. It's valid. That's where the line of best fit would hit the graph, but it's just meaningless. You don't get houses with 0 bedrooms. It's not valid, and that's all right. What's going on? There we go. And so the fact that this is a negative gradient means we've got a negative correlation. If you go on to 5, a negative correlation, and we're dealing here with humidity and visibility. Is there likely to be a causal relationship between humidity and visibility? Could anyone suggest very humid situations which might affect visibility?
Fog.
Yes. Yeah. So I reckon there is going to be a causal relationship. I'd be interested to know what they say. High levels of relative humidity can cause mist or fog, which is likely to decrease visibility. So there is likely to be a causal relationship there between humidity and visibility. There we go. Right, we'll do one more question on this next lesson, and then that's it. We'll move on. Don't need any more practice.